Dinitrogen tetroxide is shown right here, and that gets split into two nitrogen dioxide. Now here, this arrow shows that the one reaction is going into forward direction, so hence half the reaction going that way, and the other reaction is going the reverse direction. So there is this reversibility in this reaction. Let's take a closer look at this image over here. In this image, you'll see just dinitrogen tetroxide, so just that one. But over time, it starts to produce NO2, okay? And then further out, it will further turn into NO2, but sort of stays intact. The concentration of N2O4 is there, but so is NO2. And the concentration no longer changes, and N2O4 is there, and so is NO2. And they're both there. And now what's happening is every time this makes the product, well, the product reverses itself to make the reactant. There's a reversible reaction taking place, and this is a chemical reaction that goes into both forward and reverse reaction. At the point in which the forward and the reaction are equal in rate, this is considered to be at equilibrium. Remember, the rate of going forward and reversion is same. But at equilibrium, look at the concentration of the reactant and the product. So in the very beginning, you see the reactant diminishing, the N2O4. And that's because it's being utilized to make NO2. And in the beginning, there was no NO2, but it's being made as time passes because it's being produced. But at a certain point in time, the NO2 concentration does not change, and the N2O4 concentration doesn't change. It doesn't mean that the reaction has completely stopped at equilibrium. What it just means is that one is going in the forward direction, and now it's reversing back into the reverse direction. So we say at equilibrium, it is not static, but rather a dynamic equilibrium. So the concentration does not change. And it also doesn't mean that the concentration is not equal. Just because you have 50 molarity of this over time, it doesn't mean that you're going to have 25 molarity of this and 25 molarity of this. That is not the case. It is the case in which one might be higher than the other, but the concentration doesn't change. Here's a better way to illustrate equilibrium and that concentration, not changing the concentration. So say you're at a party and one side of the room is the dance floor and the other side is the snack. And the dance floor, there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 people dancing. On the snack side, there's only 2 people eating. At equilibrium, what's happened is every time that 2 people go to the right, well, the snack people will now come back and start to dance. And so now on the left-hand side, it's still 8 people, and then this will be 2 people on the snack side. It's always 8 and 2 as at equilibrium. At non-equilibrium, you would see, say, like, 5 people here, and then that means 5 people, that means 3 of them have left there, and then that means 5 over here, okay? If 3 of the people, say these 3 guys, left and go on this side right here, and there's total of 5 on the right and total of 5 on the left, it does not mean it is at equilibrium just because there are same amount of people there. It's that if there is 2 people going there, then 2 people must come here. And that needs to happen at the same time. And that is how equilibrium is at equilibrium.